Hello everyone, I am Dr. Krishna Sarker. Here in this session, I will be going to discuss about transfer function calculation from electrical networks. This is linear control systems, problem number 2. Lecture series on linear control systems, lecture number 14. So our topics transfer function calculation from electrical networks, and this is example 2. Transfer function calculation, example 2. What is the example? Find the transfer function of the given electrical networks. This is the electrical networks. Resistance R, capacitance C, and this is the input voltage Vi of t. And this is the connection diagram. V0t output voltage, V0t output voltage, and this network also called the lag networks. So Vi of t is called the input voltage and V0t is called output voltage. So this is our electrical RC lag networks. Calculate transfer function. What is the transfer function? Laplace transform of output divided by Laplace transform of input, and all initial conditions are zeros is called transfer function. Here output equals to V0t. So Laplace transform of output, that means Laplace transform of V0t divided by Laplace transform of Vit is and all initial conditions is 0 is called the transfer function. So calculate V0t by Vit Laplace transform of. Then solution. Step number 1. The given electrical networks as shown in figure A and determine the transfer function. This is the electrical network, given electrical network. This is figure number A. And in this networks, Vi of t input voltage, V0t output voltage, R equals to resistance, and capacitance, actually capacitance in this case C, capacitance equals to C, and I of t equals to current, because this is the time domain, this is the time domain. That's why capacitance C and output voltage V. Then calculate output voltage V0t divided by Vit and Laplace transform of V0t divided by Vi of t, and all initial conditions zeros. This is our figure A. Then step number 2, draw the given network figure B. This is the figure B in S domain. This is the S domain. Why S domain? Because Laplace transform of V of t equivalent to frequency domain Vi of S, and Laplace transform of V0t equivalent to Vi of S. For capacitance, this is the capacitance. For capacitance in frequency domain 1 by SC, in frequency domain 1 by SC, and I of t mesh current equivalent to I of S. That's why this is the S domain RC lag network. Then S domain with its inductance by S of SL and the each capacitance by 1 by SC. Here in this circuit, capacitance C equivalent to 1 by SC. This is the capacitance C. This is the capacitance C. Then next step, next point, use KCL, KVL, mesh analysis, nodal analysis to write network equations. So this is the loop I of t or I of S. By using KCL, KVL, mesh analysis, node analysis, write the network equations. Write the network equation. Why? Solve the simultaneous equations for the transfer function, because our target and our main focus calculation of transfer function. Then transfer function calculation. Step number 2, apply KVL in mesh 1 of the given networks. This is the given networks already discussed. Apply KVL and we get, this is the mesh number 1, we get Vi of t equivalent to RIT plus 1 by C into IT dt. This is equation number 1. This is the input voltage Vi of t, and this is the inductance, across inductance passing through current I, that's why R into I of t, and this is the capacitance C, and for capacitance 1 by C into integration IT dt. So this is for mesh 1. This is for mesh 1. Then for mesh 2, applying KVL, and we get this, the applying KVL in mesh 2. This is the mesh 2 V0T output voltage. This is the V0T. V0T equivalent to 1 by C I of t integration I of t dt, because this voltage across the capacitor, that's why V0T output voltage equivalent to 1 by C integration I of t dt, I of t dt. Then step number 3, taking Laplace transform of each equation 1 and 2 with assumption that all initial conditions are zeros. So what is the equation number 1? This is equation number 1, and this is the equation number 2, taking Laplace transform of equation 1. First taking Laplace transform of equation, and we get VIS equals to RIS plus 1 by SC into I of C. This is equation number 3. So this is the equation number 1, taking Laplace transform, and we get Vi of t, Laplace transform of Vi of t equals to VIS. R equals to constant value, and I of t, Laplace transform of I of S, and plus 1 by C constant, then integration I of t dt equivalent to Is by S, integration I of t equals to Is by S. So put here Is by S. Then taking Laplace transform both sides in equation 2, and we get taking Laplace transform both sides, V0 S equivalent to 1 by SC I of S. This is the V0T, Laplace transform of V0T equals to V0S, and this is the 1 by C constant value, 1 by C constant, and I integration I of t dt equivalent to Is by S. So this is the equation number 4. This is the equation number 4. Then step number 4, definition of transfer function. What is the definition of transfer function? Laplace transform of output divided by Laplace transform of input, provided all initial conditions zeros. Another from Laplace transform of output response of effect. Laplace transform of input variable or excitation. This is also called cause, because cause and effect relation, and all initial conditions are zeros is called a transfer function. Then by using transfer function definition, what is the step number 5? Calculation of transfer function from equation 3 and 4, and we get VIS equals to this R into IS plus 1 by SC into IS. This is equation number 3, already proved, and V0S equals to 1 by SC into IS. This is equation number 4. Therefore, equation 4 divided by equation 3, and the transfer function, TF means transfer function, is V0S by VIS, because output voltage divided by input voltage, all initial conditions are zeros. And this is the output voltage, this is the output. So this is the output, and this section input side. So this is the denominator side. This is the denominator side. From denominator come on I of S, and we get I of s common, then 1 by sc into r plus 1 by sc into I of s, I of s cancel, then v0 s by vis equals to 1 by sc, numerator 1 by sc, denominator r plus 1 by sc. This is equivalent to sc LCM, then 1 by rc into s plus 1. This is the transfer function. Output divided by input for lag network RC network. V0 S by VIS. This is in control system language. This is equivalent to actually CS by RS, because CS equals to controlled output and RS equals to reference input. RS equals to reference input. This is the transfer function. Then therefore, the transfer function of the network is given by 1 by RCS plus 1 equivalent to 1 by 1 plus ST. So T equals to what? T equals to this, T equivalent to RC. This T equivalent to time constant R into C. Time constant R into C. So V0S by VIS equals to 1 by 1 plus ST. 1 by 1 plus ST. This is the strictly proper transfer function. From the transfer function, if R equals to 1 and C equals to 1, then V0S by VIS equals to 1 by RCS plus 1, equivalent to 1 by 1 plus ST or 1 by 1 plus S, because R equals to 1 ohms and C equals to 1 farad. In this case, M less than N, because numerator power S power equivalent to 0 and denominator S power equals to 1. So N greater than M. If the order of the numerator polynomial is less than the order of the denominator polynomial, the transfer function is called strictly proper transfer function. So this is the strictly proper transfer function because numerator greater than denominator. Then V0S by VIS equals to 1 by 1 plus S. And calculation, what is the calculation? Here, number of zeros less than number of poles. That means poles greater than zeros. Here, number of poles greater than number of zeros. Number of poles greater than number of zeros. Number of poles equals to 1 at S is equal to minus 1 plus S plus 1 equals to 0 and S is equal to minus 1. So this is the pole position. And pole number of poles equals to 1, but number of zeros equals to 0. Then the above transfer function having the simple poles as S is equal to minus 1. What is the pole 0 configuration? This is the real axis, RE, and this is the imaginary axis. And poles are at only S is equal to minus 1. So put in this position, this is the pole position at S is equal to minus 1. And pole 0 concept. What is the pole 0 concept? The transfer function of a control system is defined as the ratio of the Laplace transform output response oblique effect to the Laplace transform of the variable or excitation assumption, or that all the initial conditions to be 0. This is the transfer function definition. Actually, output response by input response where all initial conditions are zeros. A 0 is indicated by the symbol, so small circle 0. And the point at which the denominator polynomial PS equals to 0 are called the poles of the system GS. Poles are indicated by small cross. Small cross. Our problem at S is equal to minus 1, only 1 poles. S is equal to minus 1. So this is the denoted by cross. This is denoted by cross. A 0, that transfer function G of S becomes 0 and at poles it becomes infinity. The denominator polynomial for the transfer function is called the characteristics equations. So thank you.